So welcome. Now from this part onwards we are going to look at microscopic balances, and as I told you, microscopic balances we are going to look at force balances, mass balances, momentum balances, but at a small control volume, differential control volume, and therefore we are going to get differential equations, and we would need to solve them to get the profile of velocity, pressure, temperature, whatever it is that we are solving for. Therefore these parts are going to be more mathematical, and therefore you have to put more efforts into solving the homework problems, doing the maths, which we will partly do in these recorded lectures, and partly it will be left for you to complete. Therefore, lot more effort now is required on your part to more understand these parts. Let's start looking at now microscopic balances. So first of all, this is where we are in our course. We are on point number 6 on microscopic balances, and we are going to use these microscopic balances to calculate some of the things that you have already seen in the macroscopic balances. But in these macroscopic balances, you have done them as an experimental value, or you have got them as an experimental value. We'll try to get more into how this can be actually calculated. I will tell you as we go along. Just to quickly revise what we have done in the previous class, write an expression for pressure drop in packed bed for particle Reynolds number less than 1. What is meant by Arkin equations? Why do particles get fluidized only beyond a certain velocity? What is this velocity called? How do we calculate bed expansion for a fluidized bed? So this will help you to revise and get in tune, or get more again into the subject, so that we can start with microscopic balances. So first thing that we are going to do is look at laminar flow in microscopic balances. So remember, this was the video that we saw for laminar pipe flow. You can see that these the fluid, or the liquid in this particular case, is moving layer like. So what we are going to do first of all is how much force is experienced by one layer sliding over another layer. So imagine that these are the two layers, and then one layer is going faster, slightly faster, because it is maybe near the center of the pipe. One layer may be near the wall of the pipe, that is moving slower. We have seen that when we talked about velocity profiles. So first of all, what we are going to look at is how much force is experienced by one layer sliding over another layer. What is the reason for that? What is the reason for that force, and how do we quantify that force, and then how do we use that to get the important details like pressure drop, friction factor, and so on. So imagine that we have different layers like this. I'm just showing you 3 layers. Let's say this is layer 1, this is layer 2, and layer 3. Okay, let's take some coordinate axis. Let's say this is our x coordinate, and this is our y coordinate. This is our z coordinate. So we are taking Cartesian coordinate system. Let's not worry too much about z just now. But what we are trying to say is that velocity profile we have like this. So Vx is a function of y. That's what is the meaning of this expression. Again, recall, these are velocity vectors. So for example, here the velocity is in the x direction. The direction of the arrow shows the direction of the velocity, and length of the arrow shows the magnitude of the velocity. That is the meaning of the vector. That's how we have been drawing vectors, right, from 11th standard. So here at this point, velocity is in this direction. It has a magnitude corresponding to this. So velocity is higher at this location, velocity is lower at this location, velocity is still lower at this location. So we are saying that Vx changes with y. That means Vx is a function of y. Now imagine right now that this is not a liquid, but imagine right now this fluid is a gas. So we have a gas here, and recall from your kinetic theory that these gases have a, a random thermal motion. So what we are looking at is we are looking at two kinds of motion. One is a random thermal motion of the molecules, and second is the directional motion arising out of the velocity that that velocity field that we have. For example, if you are let's say there is a fan that is running in your room, so this fan is directing the air downwards, right? So the fan is giving this air some velocity. Let's say velocity is 1 meter per second here, 1.5 meter per second here, 2 meters per second here, and so on. That means velocity is in the x direction. Let's say this is our x direction, so velocity is in the x direction. Velocity in the x direction at this point is say 1 meter per second, 1.5 meter per second, 2 meters per second. Okay, and let's say if this direction is y, that means this velocity is varying with y. Vx is a function of y. That is what is the meaning of that expression. Now recall, so this is one motion that is induced by the fan, let's say. So this is called as a net motion, or this is the mean velocity, or this is the bulk flow that is caused by this fan. It is a unidirectional velocity. We call it as a convection. It is the velocity that is created by fan, by wind, by temperature gradient, by whatever means, by pressure, by pump, whatever. So when you have a fluid flowing through a pipe, pump is giving energy, and the all molecules are moving along the pipe. That's the convection. That is the net motion created by that pressure difference, and that's called as convection. And there are, besides this convection, that's the net motion. Each molecule at any location has a random thermal motion. So we are looking at two kinds of motion. One is the motion created by the external force, could be pressure, could be fan, could be wind, could be gravity, could be anything. Second is a random thermal motion, and these molecules are moving at random. Now what this is going to do is, imagine now that these are the molecules. So this is, let's say this is one molecule. So this molecule, let's say there is a fan here if you like. So this molecule is propelled down to the right, let's say with a velocity 1 meter per second. But this molecule also has a random thermal motion, right? And arising out of that random thermal motion, it can travel to other location and collide with the molecules there. So now if it's a gas, the distance between these two successive collisions we call, or it is related to the mean free path. So what we are going to look at is how much momentum this molecule is carrying, how much momentum this molecule is carrying here, which is over and above the momentum that was originally at this location. Okay, so if m is the mass of the molecule, this molecule has a momentum in the x direction. Now we are going to, momentum is a vector, so we are going to talk about momentum now in the x direction caused by this fan, if you like, which is causing this velocity profile to be there. So let's say this molecule now has a momentum in the x direction equal to mass of that molecule multiplied by velocity in the x direction. That's why this is the momentum in the x direction. But this is measured at y minus delta y at this location. So this vertical line means where this value mvx is calculated. So this mvx is calculated at a location y minus delta y. Right? Now suppose this molecule is moving in the y direction. It is going and transferring its momentum to the liquid or to the other molecules that are there. Therefore this molecule is transferring momentum. So this is transport of momentum by molecular motion. That's why this subject is called as momentum transfer. Okay, so we are going to write mathematically how much momentum is carried by one such molecule traveling from here to another location y. Okay, let's do that now. So now the rate of change of momentum in the x direction, so we are going to say x momentum, meaning momentum in the x direction. Now where is this momentum getting transferred? It is transferred to a plane at y. That plane at y is this plane, right? What is the area of this plane? The area of this plane is the distance in the x direction and distance in the z direction. It would have a distance, some width in the z direction. So area of this plane is the its distance in the x direction and its distance in the, or its length in the x direction and its length in the z direction. Try to visualize. That's why engineering graphics subject was there, to help you to visualize all this. Okay, so how much momentum it is going to carry? It is going to carry the momentum that all molecules traveling in the positive y direction minus the x momentum of molecules traveling in the opposite direction. Means they are whichever molecules are traveling in the y direction, right, and whatever positive y direction, and all the molecules that are traveling in the negative y direction. That's the net change of momentum that is experienced by this. That's the rate of transfer of momentum by motion of all such molecules. Okay, so if we write, so remember kinetic theory of gases. So if we had one molecule, that one molecule will transfer a momentum equal to m into vx at y minus delta y in the positive y direction minus m into vx at y plus delta y, traveling in the opposite direction. It is traveling in the opposite direction. This is traveling in the upward direction, positive y direction. Such molecule, because molecules are there everywhere, they would have random thermal energy. They will travel. Some of the molecules will travel from here to here also. Some of the molecules will go from here to here. But the net momentum that they are carrying is this minus this. So this, whatever mvx at y minus delta y minus mvx at y plus delta y. That's the net momentum that one such molecule will carry. What is now the rate of change of momentum per unit area? Per unit area of the plane, not plane. It is not play. It is plane. So what is the net rate of change of momentum at the plane y? At the plane y, if one molecule is transferring momentum, we need to multiply that by how many collisions are there, how many molecules are colliding per unit area. So in kinetic theory of gases, we had used the term, or we had used the symbol Z to denote how many such collisions are happening per unit area. So if you look at the right hand side here, Z multiplied by this term tells you how many such collisions are transferring momentum to this plane at y per unit time per unit area. So this is transfer of momentum due to one molecule multiplied by number of molecules colliding per unit time per unit area. So this is net rate of change of momentum per unit area, and rate of change of momentum per unit area is nothing but force per unit area. We are going to call this force as tau yx. We are going to call it as stress, right? Remember again, why we are calling it as stress and not pressure is because this is the plane that we are considering. We are considering one such plane. And molecules are colliding. They are bringing x momentum. So the force that is experienced by these molecules is in the by this plane at y is in the x direction. Therefore, whereas pressure we consider as force perpendicular to the wall, this force is in the plane, is in the direction of the plane. Therefore, we do not call it as pressure, we call it as stress. Think about it this way, as let's say three of you are standing in a row. Person is here, another person is here, another person is here. This person is moving at 1 meter per second, this person is moving at 0.5 meters per second, and this person is stationary. And all three are holding hands. So if this person is moving at 1 meter per second, it is going to pull this person, and this person is going to get pulled in the x direction. Same way, when molecules transfer momentum, they are causing a force in the same direction in which they have a momentum. We are talking about the x momentum. So therefore this is a force in the x direction. Therefore it is not called as pressure, we call it as a stress. We denote this stress as yx. Okay. Another thing to remember, why this yx, we are talking about momentum in x direction, that's why this subscript x. And this transfer of momentum has occurred because molecule has moved in the y direction. Therefore we are going to call this stress as tau yx. Another way of saying is, this is the momentum in the x direction, it has been transferred because of velocity gradient in the y direction, because vx is changing as a function of y. So if you like, this y is denoting what is the, in which direction is the variation of vx, and this force is in the x direction, therefore we are going to call this as tau y and x. Now you've seen Taylor series. What we are going to do is, we are going to Taylor series is f of x would be equal to f of x naught plus delta x times f dash x naught plus delta x square by 2 factorial, double derivative, second derivative of f at x naught, and so on so forth. We are going to write this Taylor series now for this vx at y minus delta y. So just let me write for one case, vx at y minus delta y. I'm going to write a Taylor series for this. Vx at y minus delta y would be equal to Vx at y plus delta y. Now delta y is negative, therefore that minus delta y. If you like, you want to write plus, write plus here and write it as minus here, minus delta y into derivative of Vx, dvx. Now derivative is with respect to what? It is with respect to the direction, the velocity gradient. It is dvx by dy. It is gradient. The variation we are writing, the Taylor series we are writing, is because of this variation delta y. Therefore it is dvx by dy plus delta y square, now minus delta y square by 2 factorial, double derivative d square vx by dy square, and so on so forth, right? So we are going to neglect all these higher derivatives. So all these higher derivatives we are going to neglect. We are only going to keep this as a simplified version of the Taylor series. Same way we can do a Taylor series for Vx at y plus delta y. That will be Vx at y plus delta y dvx by dy. There is a minus sign here. And remember, when you talked about kinetic theory of gases, the collisions, the distance in the y direction was 2/3 of the mean free path. Lambda was the mean free path. Now we can substitute all that, and from kinetic theory, z is 1/4 n u. U is the RMS velocity, and RMS velocity is coming from this kinetic theory of gases. K is our Boltzmann constant. Take care of the units. So J by K, it is joules per Kelvin. That's the Boltzmann constant. R by Avogadro number. So I take Avogadro number because it's in joules. It has SI unit. So take mass in kilograms. You will need Avogadro number as 6.023 into 10 raised to 26. So be careful about the units. And lambda, the mean free path, is going to can be written as root 2 pi d square n. So d is the collision cross section. Don't worry about too much about all this. This is all coming from kinetic theory of gases, because we are assuming that right now we are writing this for a gas, and this gas is obeying ideal gas law. So this random thermal motion which is causing the molecule to transfer its momentum in the y direction, to transfer its momentum in y direction, is because of the random thermal motion, and the random thermal motion is given by the RMS velocity of the molecules, right? Now, so if you simplify, if you substitute all this, substitute for z, right? Substitute for z here, do Taylor series expansion and simplify. What you will find is that the tau ix is equal to minus 1 by 3 n number of molecules per unit volume, mass of molecule, RMS velocity, mean free path. We have substituted that from this delta y. This delta y is 2 by 3 lambda. Okay, derive this yourself, make sure that you get it, and it is dvx by dy. So now all this I can club into a constant because they are constant for a particular gas at a particular temperature and pressure. 1 by 3 is coming from the mean free path. Number of molecules per unit volume, that depends on the pressure of the gas. M, mass of the molecule, that depends on the gas. U, RMS velocity, that depends on the temperature, mass of the molecule from here. And lambda, the mean free path, again depends on number of molecules per unit volume, right? So I can write this tau ix as some constant which is accounting for all of this multiplied by dvx by dy. This you might have heard or studied some point of time as Newton's law of viscosity. Newton's law of viscosity. And this viscosity is related to how many molecules are there per unit volume, what is the mass of the molecule, what is the RMS velocity, what is the mean free path of the molecule, and n multiplied by m we can as well write as density of the gas multiplied by RMS velocity multiplied by the length through which they travel between successive collision. Therefore it is related to the mean free path. So what what we are trying to say, let's try to think besides the mathematics, let's try to physically imagine and understand what we are trying to say. We are saying that there is a plane, there is another plane, this plane is moving at a certain velocity, this plane is moving at a certain velocity, molecules here have random thermal motion. This random thermal motion is taking molecules to this plane and exchanging momentum here, and the difference in the momentum is what is the net transfer of momentum. That is the what is causing the plane to be pulled, plane to experience a force in the direction in which these planes were moving. These planes were moving at different velocities, but they were moving in one direction, some direction. The plane is therefore experiencing a force in that direction, and therefore that is called as a stress. It is not a pressure, it is not a perpendicular force arising out of molecular collision. That is pressure. This is because of the transfer of momentum, and that transfer of momentum is because of random thermal motion. It is because of molecular motion. It is because of the molecular motion. So viscosity is because of the molecular motion. It is representing as if there is a pull on a slower moving layer by a faster moving layer, or a slower moving layer is tending to pull back, drag the faster moving layer. So this is the force that is experienced by when one layer is trying to move over another layer. And that is the origin of friction between these layers. Okay? If you want, pause this video, think about all the things that we have talked about so far. It's a good idea. You might be wanting to pause the video, think about all the things that we have said so far, re-look at all of them, and really try to understand what we are trying to mean. First of all, physically understand, and then secondly, mathematically understand. And once you understand, then go forward in the video. Okay, these are very serious and slightly advanced concepts. Take your time to understand all these concepts. Okay, let's go forward. So what we have said is tau ix, the stress, is equal to minus mu dvx by dy. Dvx by dy is like the strain rate, deformation of the fluid element. Right? So let's try to visualize that as well. Let's try to visualize that deformation. Suppose this is one packet of fluid, right? imagine that, let's look at it from this angle. Let's say these are the two layers. This is the top layer of the fluid. These are the two layers, one layer top, one layer at the bottom. So imagine this direction is the Vx direction and this direction is the y direction. Now what we are saying, Vx is a function of y, means what? The top layer is moving at a different velocity than the bottom layer. So if you think about this packet, one layer is moving faster than the other. This packet of fluid is going to get deformed. You see the change of shape? It was like this. Okay. It is going to get deformed. Let's not try to rotate it. Let's only try to deform it. You see the deformation? That is the meaning of the deformation. That is the meaning of the strain that the fluid experiences. dvx divided by dy. Okay. That is the meaning of deformation. Okay, let's go forward now. So this dvx by dy is the strain rate or deformation. It is denoted by a symbol gamma or sometimes gamma dot because it is called as rate, strain rate. Now, little bit about this minus sign as well. What was our Vx? Our Vx with respect to y, this was the x direction. Our Vx was reducing in the y direction. Vx was reducing in the y direction, which means this dvx by dy had a negative sign. It was, slope is negative. Slope is like this. dvx by dy is the slope of this line, and the slope of this line is negative, and this force is in the positive x direction. It is in the positive x direction. That's the force on one layer. Correct? So therefore this negative sign is coming, that whenever that velocity gradient is negative, the force is in the positive x direction. That's why that negative sign is coming. Now we have been talking about, rather than talking about Vx, we would rather talk about as rho Vx. So I can take this expression, multiply and divide by rho. So I can write mu by rho d by dy of rho Vx. Now rho Vx is momentum in the x direction per unit volume of the fluid, and this mu by rho we can call as kinematic viscosity. So we are going to define two kinds of viscosities, one the dynamic viscosity and one kinematic viscosity. Dynamic viscosity we are going to write by symbol mu. It has units of Pascal second. Now let's see that as well. Tau yx has a unit of Newton per meter square. Right? So tau yx has a unit of Newton per meter. So let's write it here. Tau yx has a unit of Newton per meter square. Right? That is stress. Mu. dvx by dy. This is the unit of stress. dvx by dy. What is the unit of dvx by dy? dvx is meter per second. Y is meter. So this is unit of 1 per second. Strain rate. That's why sometimes it is called as strain rate. And therefore mu will have units of Newton per meter square multiplied by second or Pascal second. Newton per meter square into second. And Newton also we can write in terms of kilogram meter per second square. This would be kilogram per meter per second. That would have the unit, that will be the unit of viscosity. Now kinematic viscosity mu by rho, it will have unit of meter square per second. Right? Just check that for yourself from here. And this is like diffusivity for momentum, and diffusivity for momentum is like u by lambda. Remember, if your mu from here, mu by rho would be like u multiplied by lambda. U multiplied by lambda is u, of course that 1/3 factor is there, don't worry about that just now. U, the RMS velocity meter per second, lambda distance meter, so it will have unit of meter square per second. It is called as diffusivity for momentum. We'll see this later when we start talking about heat transfer and mass transfer, and see how these are all related to each other, how these are analogous to each other. Again, so now if the viscosity is higher, to get the same flow, I would produce a higher stress or a higher force that this liquid has to, or this fluid has to be, the force between layer would be higher, and therefore I would require larger energy or larger power to make the layers slide over one another at the same rate. And therefore higher viscosity liquids or higher viscosity fluids require more energy or more power for flow. So recall our video from mixing coffee in milk or mixing of two paints. It was more viscous, right? Now we can see the meaning of that viscous. It required more force to get the same level of deformation in a paint as compared to a coffee or water or soup, let's say. Okay. So again, so this stress, so just some typical values of viscosity. Air typically has a viscosity of 2 into 10 raised to minus 5 pascal second. It's at room temperature and pressure. Water typically at 30 degrees centigrade has a viscosity of 0.9 into 10 raised to minus 3 pascal second. If you just want to approximate 1 into 10 raised to minus 3 pascals per second, and therefore 1 into 10 raised to minus 3, we can, this is approximately, if we are talking about 20-25 degrees centigrade, it is typically 1 millipascal second, 10 raised to minus 3 pascal second. That's typically the viscosity of water. That's what we take for simplified calculation. Here are just some graphs of how this viscosity changes with respect to temperature, right? So this is the dynamic viscosity in terms of millipascal second. The graph is not very clear, but you might have to zoom in and see for yourself, versus temperature. And you see how exponentially this curve falls, how exponentially the viscosity of water reduces with temperature, liquid water. So typically liquids viscosity decreases very rapidly with temperature, very sharp decrease. So sometimes when you want to transport viscous liquids, you heat them up before transferring. Say for example, you want to transfer maybe some glycerol or some polyethylene glycol, some polymers you want to transport. Rather than transporting them at lower temperature, you might want to heat them up slightly, maybe 70-80 degrees and so on and so forth, and then they get transferred easily because their viscosity drops very dramatically with temperature. Whereas for gases, we have seen that it is related to the kinetic theory of gases, right? So liquids, in this is not applicable for liquids. The kinetic theory of gases is not applicable for liquids. So this expression is not applicable for liquids. For liquids, we have to think about something else, right? That not for liquids. It is only applicable for gases, that two gases which are obeying kinetic theory of gas, which means they behave like ideal gas, which means they are at high temperature and low pressure, not for liquids. Why? Because sometimes the liquid molecule, let's say it's a polymeric molecule, so then this molecule itself can be as big as the distance between the collisions, and molecules of the liquid are close to each other. So molecular size and their mean free path, they can be comparable to each other. Therefore only part of the molecule may collide, right? They don't have to really travel a great distance. They are maybe vibrating. That's why this is not applicable for liquids. We'll talk about that as we go a little bit further. For gases, you can see viscosity is proportional to U bar and lambda and Nm. M of course is the same, but N, density of the gas. So this U bar increases with temperature, right? So the kinematic viscosity or the molecular viscosity or dynamic viscosity, that typically increases with temperature. So that's the difference between a gas and a liquid. Viscosity will increase with temperature for a gas. Viscosity will reduce very dramatically with temperature for a liquid. Okay, let's go forward. So we are going to call these stress-strain relationships as constitutive equation, and this constitutive equation is linear right now. Stress-strain behavior is linear, and any such fluid that behaves like this is called as a Newtonian fluid. Newtonian, it behaves Newton's law of viscosity. Newtonian. So most liquids that you will come across in everyday life are Newtonian. Water, air, all gases, LPG, CNG, all those gases, they are Newtonian. Liquids, most of the liquids that you will come across, water and so on and so forth, is Newtonian. Benzene, toluene, lower organics, acetone, ethanol, methanol, toluene, benzene, xylene, these are all Newtonian. They are all fairly simple molecules. But if you talk about polymeric materials, polymeric solutions, they don't behave like this. Then they are called as, if this is not valid, then these are called as non-Newtonian fluids. And we'll see about them later on. Okay, so right now let me rub out this not equal sign and let me rub out this non word as well. Okay, now again imagine that this fluid element that we have seen, okay, Vx changing with y, or Vy changing with x. Vy is also changing with x. So this is Vy at this location, this is Vy at this location. So Vy is changing with x, it is deforming. Okay, or Vx changing with y, it is deforming. Now imagine that both things are there. Vx as a function of y is also there, and Vy as a function of x also is there, right? So what we are saying is, if I take this fluid element, at this location there is Vx, at this location there is a slightly different Vx. It is given by Vx multiplied by this delta y multiplied by the gradient dVx by dy. There is Vy here. At this face, at this plane, the value is slightly different. It is Vy plus delta x multiplied by dvy by dx. Now this is going to do two things. One is, of course, suppose this is the center of the fluid element. Suppose this is the center of the fluid element. Okay. So this velocity, the force here is going to cause a net torque in this direction. The force here is going to cause a net torque in this direction, and the resulting force or a resulting torque is going to cause a rotation of this fluid element about its axis. So the rotation is going to be related to the difference between the two velocity gradients. That's going to cause rotation. But both these gradients are going to deform this direction as well as this direction. So there is a net deformation. So there is going to be a net deformation, and then there is going to be a net rotation. The net deformation we can write like this. Therefore tau yx we write as minus mu times dvx by dy plus dvy by dx. So far we had only considered one velocity gradient. We had only Vx as a function of y. Now we are going to have to consider both Vx changing with y and Vy changing with x. So there is a net deformation and then there is a net rotation. Now if you think about all such directions, we can define all such values of stress. Let me show that in the next slide. Okay, so imagine here is a fluid element, x direction, y direction, z direction. Imagine this is the fluid element, and Vx also is there, Vy also is there, Vz also is there, and Vx changes with x, y and z, Vy changes with x, y and z, Vz changes with x, y and z. So all the all the velocities are moving or are varying in all the three directions. What we had seen just now was the plane in the y direction. We had only seen this plane. We had only seen this plane. This plane was equivalent to this top surface and this bottom surface. So the tau yx is going to act on this top surface in this x direction. Tau yx is going to act on this plane in this direction. Similarly, if you consider the front face of this fluid element and the back face of this fluid element, if Vx changes with Z, this front face will experience a force tau Zx. The back face will experience a force tau Zx. Again, tau Yx is the force experienced because of dVx, because of Vx variation with y, dVx by dy. It is acting on the top face and the bottom face. Tau Zx is the force experienced in the x direction because of Vx varying in the z direction. That force is going to be experienced, or that force is going to be present on the front face and the back face. Try to visualize all this for yourself. It takes time to visualize. Now suppose the flow is like this. Let's say we are talking about orifice meter. Okay, there is a pipe here, there is an orifice meter here, orifice here. The flow is going in all this direction, right? We said that cross-sectional area is reducing. Cross-sectional area is reducing, velocity is increasing from here to here, from here to here, velocity is increasing. And if we say that this is our x direction, can we not say dvx by dx is non-zero here? Same way, if you look at the orifice part and the pressure recovery part here, say let's take a point here and point here. Let's call this as point number 2 and let's call this as point number 3. Between 2 and 3, can we say Vx is reducing, which means dVx by dx is non-zero? Between 1 and 2, Vx is increasing in the x direction, which means dVx by dx is there. Now Vx increasing with x direction, that means if you think about this, that means this part, suppose this is our x direction, right? Suppose this is our x direction. The front part is getting pulled faster than the rear part of this fluid element. It is going to cause shear, it is going to cause elongation. If you imagine an elastic band, if this was an elastic band, you can stretch that elastic band. That elastic band stretching happens between 1 and 2. If you talk about 2 and 3, velocity at the 2 is lower, velocity at 2 is higher, velocity at 3 is lesser. It is going to cause compression of this elastic band. Try to visualize that. So dvx by dx non-zero can lead to elongation or compression. We call that as a elongational or compression stress. We denote that right now, we are going to denote that by sigma xx. So that sigma xx, because of dvx by dx, it will act on the right face of this element and the left face of this element. Okay, try to visualize that. Right now I am going to show this elongational stress or compression stress by a symbol sigma, just to differentiate it from the shear tau yx and tau zx. So right now in the x direction, what stresses we have seen? In the x direction, there is a tau yx, there is a tau zx, and there is a sigma xx. So these are the stresses in the x direction. If you think about y direction, let's take another color. If you think about the y direction now, Vy varying with x, Vy varying with x, that is given by stress tau xy. That will be experienced on the right face and the left face, tau xy. Similarly, Vy varying with z, Vy varying with z, that will lead to a stress tau zy. It will be experienced on the front face and the back face, tau zy. And sigma yy, elongation or compression in the y direction, sigma yy, that will be experienced in the y direction, that is the sigma yy. It will be experienced on the top face and the bottom face. Let's look at the z direction. Let's take another color. Let's look at the z direction. Vz varying with x, Vz varying with x, that will lead to a stress tau zx. Let's take a nice color. Red we have done, green we have done. Let's see, maybe purple. Let's see, the purple is visible. Yeah, okay. Tau xz. That is because Vz varying with x. That is going to be experienced in the z direction. It is going to be experienced on the right face and the left face. Vz varying with y, it is tau yz. Vz varying with y, it is going to be in the z direction. It is going to be experienced on the top face and the bottom face. Elongation and compression, tau zz, elongation and compression, Vz varying with z, we are going to call that as sigma zz. It is going to be experienced on the front face and the back face. Okay. Remember this, wherever we are talking about tau yx, tau zx, sigma xx, this is the force in the x direction. It is the force in the x direction. Tau xy, tau yy, tau zy, it is the force in the y direction. Tau xz, tau yz, tau zz is the force in the z direction. Tau yx, it is going to be experienced. Let's rub out all this now. It's too many things. Tau yx, tau yx. Look at this tau yx, what we had. Tau yx was acting on this plane at constant y, which means it was acting on a plane which was perpendicular to the y axis. Tau yx is going to act on a plane perpendicular to the y axis. It is going to have an area delta x delta z. Tau yx is going to act on a plane perpendicular to y. Plane perpendicular to y, it's going to have an area delta x delta z, which is the top face and the bottom face. Tau zx is a plane at a constant z. It is going to be in direction perpendicular to the z. That is nothing but the front face and the back face. Tau xx, which means it is perpendicular to the x axis, which means it will have an area delta y delta z. It is in the left face and the right face. So think about all these. This whole 9 terms, they are called as stress tensor. 3 directions, x direction, y direction, z direction, arising out of the velocity gradient in x direction, y direction, z direction. 9 terms. The diagonal terms are the compression or the elongation. They are called as normal stresses. Right now we are going to denote them by sigma, but later on we will just say tau. The off diagonal terms are called as shear stresses. And this stress tensor is symmetric because we have said tau yx is dvx by dy plus dvy by dx, which means that tau yx and tau xy are identical. Let me rub all this now. Tau yx and tau xy, they are identical. Tau xz and tau zx are identical. They are the same. It's a symmetric tensor. Tau yz and tau zy, they are the same. It's a symmetric tensor. So that's what's the meaning. The tensor is symmetric. Okay. Try to visualize all this. Okay. Try to visualize this. Every face you should be able to visualize. If you want, make a box out of a cardboard or something, and on each face you write what forces are going to act. Right. Try to make this make a physical model of this. Okay. And keep it wherever you go often. Just keep this, let this get bombarded into your system, right? Visualize all this. Let's go forward. So Bert Stuart Lightfoot's book Transport Phenomena, appendix B1 gives all these stress strain relationships for Newtonian fluids. You can see these are in the Cartesian coordinate system. We have talked about Cartesian coordinate system only right now. But we could have a cylindrical coordinate system. If you are talking about this pipe, we could have z direction. Let's take another color. We could have if we are talking about the axis of the pipe, along the axis we have the z direction. Away from the axis we have the r direction. Around, away from the axis, it is the r direction, and around the axis we have theta direction. So that's called as a cylindrical coordinate system. Okay, so just like we have stresses tau yx, tau xy in the Cartesian coordinate system, we would have stresses in the cylindrical coordinate system as well. Okay. They are going to be like tau rz, tau zr, tau theta z, tau z theta, tau r theta, tau theta r, tau r, tau theta theta, tau z z. Don't worry too much about where these things come from, but you see these expressions. Okay, so in a cylindrical coordinate system now, try to visualize the differential element and try to visualize the stresses like this. Make a physical model of this. Make a box out of something. Make a box. You might have a box for something that you got from Amazon or something like that. Give some names X, Y, Z and draw all these stresses on the box so that you are able to visualize. Because what we are going to do in the next lecture is write a force balance on one such box. Okay, therefore it is important that we visualize all this for ourselves, because it is going to help us to write the force balances, write the forces. Okay. All the things that we have talked about so far, they are from Transport Phenomena, Bert Stuart Lightfoot's book, affectionately called as BSL. World over it is known as BSL. We are on chapter 1, sections 1.1 to 1.4 and appendix B1 tells you all these relationships from the stress strain relationships. Okay. What we have covered so far, we have tried to look at a differential element, differential box, and we have tried to look at forces arising out of molecular motion, the molecular motion, laminar flow, layer-like motion, how momentum is transferred because of molecular motion across layers. That is the reason for the force. That is what we have covered so far. Next lecture, what we are going to do is try to write all the forces acting on that box. We have only considered the viscous force. We have only considered force due to molecular motion. We have only considered viscosity. We have only considered diffusivity of momentum. Other forces we need to consider, right? Those we will consider and write a balance for that whole box. That's what we are going to do in the next class.